Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of alien mathematics, high-dimensional architecture teardown. In this page, we will cover the fundamental disconnect between our biological hardware and the next-generation environment of high-dimensional mathematical reality. Our brains are essentially legacy hardware, optimized over millions of years to navigate a three-dimensional world and a linear flow of time. While this served our ancestors well for survival, it poses a significant bottleneck when we try to grasp the true nature of complex systems. The image shows a human brain encased within a nested cube structure, illustrating how our cognition is trapped within limited spatial dimensions. Beyond this lies an infinite stack of cubes representing n-dimensional space. We are moving from a world we can visualize to one we can only process through advanced computation. This journey requires us to look at the new stack of technology that allows us to interface with realities that exist far beyond our natural senses. We are moving past linear time into a realm where variables interact in ways that no human mind can naturally simulate. Welcome to the team as we explore these high-dimensional architectures. The second page explores the concept of the legacy constraint, specifically what we call the biological three-dimensional trap. Human cognitive chunking relies heavily on physical analogies because we understand best what we can touch and see. However, when we try to input quantum or biological scale problems into this framework, we hit a massive dependency error. The diagram illustrates an input being pushed through a process of Newtonian and Euclidean analogies, only to result in a translation failure against a literal brick wall. This represents the reality that translating a 150-dimensional quantum state into a three-dimensional human intuition is far too lossy to compile. We lose the essential details that make the system work. We cannot simply use our common sense to solve problems at this scale because our common sense was never designed for it. This failure of translation is the primary hurdle in modern scientific advancement. We are trying to use a language of physical blocks to describe a reality of complex multidimensional vibrations and probabilities. In page 3, we discuss the time complexity failure known as Levinthal's paradox. This is a fundamental problem in protein folding and other complex systems where the total possible states are astronomically high. For a single protein, there might be 10 to the power of 300 possible configurations. Even with a processing speed of 10 to the power of 13 configurations per second, it would take 10 to the power of 27 years to execute a brute force search. This is a timeout error because the execution time exceeds the age of the universe. The visualization shows a massive branching tree of possibilities with a red line indicating a failed path. This proves that you cannot brute force your way through the universe using legacy algorithms. The hardware of the universe is simply not fast enough for that approach. We need a new kind of algorithm that does not rely on checking every single state, but instead finds a shortcut through the high-dimensional landscape. This realization is what led to the development of the revolutionary architectures we use today. The fourth page provides a system tear down of the AlphaFold architecture. This system represents a major shift in how we approach science. It does not simulate folding physics in the way a human would by calculating every force and bond. Instead, it bypasses physics entirely by learning the statistical patterns of nature. The process begins with an input of a linear amino acid sequence, which is then fed into Module 1 for evolutionary history and statistical pattern matching. From there, it enters the Evoformer, which is the heart of the system. This leads to the SE3 equivariant transformer, which finally outputs a three-dimensional protein geometry. To date, over 200 million proteins have been cataloged using this method. This architecture proves that we can achieve accurate results without needing to understand the underlying physical step-by-step mechanics, as long as the machine can identify the high-dimensional patterns that govern the final shape. It is a transition from mechanistic understanding to statistical mastery. Page 5 focuses on component A, which is the Evoformer and its use of high-dimensional data structures. The main takeaway here is to forget everything you learned about traditional three-dimensional physics engines. The data structure used here is an abstract mathematical object that maps pairwise relationships simultaneously across 48 Evoformer blocks. The input consists of pairwise amino acid relationships, which are then processed through a dense grid of neural weights. One of the most striking points here is that the interpretability of this system is 0%. The representations are purely neural weights. They are not human concepts like hydrogen bonds or beta sheets. While a human scientist looks for specific chemical interactions, the Evoformer looks at a massive matrix of abstract connections. It creates a mathematical landscape that is highly effective for prediction, but completely opaque to human intuition. We are trading our ability to explain the process for the ability to achieve a perfect result. In page 6, we examine component B, the SE3 equivariant transformers. This is the engineering layer that acts as a translation layer. It reasons directly in three-dimensional space by treating geometry as the fundamental object of computation. Its function is to compute the final geometric configuration from the high-dimensional representation provided by the Evoformer. The caveat here is that, while it gives us the map, it does not provide the coordinates in a way we can easily use. We get the exact answer without the how. The target is the geometry itself, viewed through the lens of mathematical transformations. This module ensures that the predictions remain consistent regardless of how the protein is rotated or moved in space, which is a key requirement for physical accuracy. It bridges the gap between the abstract math of the Evoformer and the physical reality of a protein structure, even if the internal logic of that bridge remains hidden from us. Page 7 introduces our second system teardown, which is alpha geometry. This is a neurosymbolic hybrid system that mimics the relationship between human intuition and rigorous logic. It represents a shift from simple calculation to complex deduction, with the task of solving international mathematical Olympiad-level geometric proofs. The diagram shows two pistons working together, a neural language model and a symbolic engine. We are combining intuitive, probabilistic leaps with strict, deterministic logic gates. This is where the machine starts doing real math rather than just pattern matching. The neural side suggests potential moves or constructions, while the symbolic side verifies them against the rules of geometry. This partnership allows the AI to navigate through vast search spaces that would paralyze a purely symbolic system while maintaining a level of rigor that a purely neural system could never achieve. It is a powerful synergy that represents the future of automated reasoning. The 8th page focuses on component A of the alpha geometry system, the symbolic deduction engine. This is the side of the machine that generates proofs that are formally unassailable. It is essentially the engine of certainty. Its function is to apply precise inference rules in a completely deterministic manner. The output status is 100% verifiable, rigorous, and logically sound. Unlike neural models that can hallucinate or give approximate answers, the symbolic engine operates on the bedrock of mathematical truth. If it produces a proof, that proof is guaranteed to be correct according to the axioms of the system. This part of the architecture provides the guardrails for the entire process, ensuring that the creative leaps taken by the neural side do not lead into logical dead ends. It represents the classical side of mathematics, where every step must be justified and every conclusion must follow inevitably from the premises. Page 9 explores component B, the neural intuition model. This is what we call the alien leap. When the deduction engine stalls because it cannot find a path forward, the neural model suggests auxiliary points or constructions that are often invisible to human intuition. It navigates a geometry of thought that we cannot see. The training set for this model consists of 1 billion synthetic diagrams, allowing it to develop a deep sense of geometric possibility. The moves it suggests are valid, but often totally bizarre to a human mathematician. It might suggest drawing a circle in a place that seems irrelevant, only for that circle to become the key to the entire proof. This is where the machine demonstrates a form of creativity that is not bound by human cognitive biases or established teaching methods. It is an exploration of the mathematical landscape that goes beyond the paths we have cleared over centuries. In page 10, we look at system integration and the concept of compiling hyperlogic. The AI is not simply mimicking human logic. Instead, it generates a high-dimensional vector signature that acts as a hyperlogic pathway. This is an intuition we cannot compile in our own heads. The performance metrics are impressive, with 25 out of 30 IMO geometry problems solved. This benchmark, known as AlphaProof, achieves the equivalent of an International Mathematical Olympiad silver medal. The visualization shows a beam of light cutting straight through a complex maze, bypassing the traditional walls of logic. This illustrates how the system finds direct routes to solutions that appear convoluted or impossible to us. We are seeing the emergence of a new kind of intelligence that solves problems by seeing the maze from a higher dimension, allowing it to move through barriers that stop us in our tracks. Page 11 discusses a critical failure point known as the transparency crisis. As AI becomes more powerful, we risk entering a scientific dark age where we possess the answers but lack the cognitive capacity to understand the explanation. Consider a scenario where an AI proves the Riemann hypothesis. The output might be a 5 million line proof existing in a 100-dimensional space. While the proof is mathematically valid, no human being could ever read or comprehend it in a single lifetime. We become users of the technology rather than knowers of the truth. We have the cure for the disease without understanding how the cure actually works. This creates a fundamental gap in our knowledge. We are building oracles that give us the truth, but we are losing the story that connects our observations to our understanding. It is a profound shift in the nature of human knowledge. The 12th page covers system dependency and formal verification, which acts as a sanity check. In this stage, we use protocols like lean or cockproof assistance to machine check logic that humans cannot read. This is a critical engineering note. Verification does not equal comprehension. We can mathematically confirm that the oracle is not hallucinating, but the verifier provides zero illumination. It checks the math, but it does not explain it. The diagram shows a complex mechanical heart inside a glass box, producing a valid checkmark. We can trust the result because the machine says the logic follows the rules, but we are still left in the dark regarding the underlying meaning. This is a necessary step for ensuring safety and accuracy in high-stakes environments, but it highlights the growing divide between what we can prove and what we can actually understand as biological beings. Page 13 addresses emergent bugs and unintended behaviors. These are risks that arise from the structure of the model rather than explicit programming. Because these models are so complex, subtle errors can be embedded within the unreadable logic, leading to what we call opacity risk. You are trusting an emergent property, not a programmed function. This is the very thing that makes these models powerful, but it also makes them dangerous. If a model develops a shortcut that works most of the time, but fails in a catastrophic way under specific conditions, we might not be able to find that flaw until it is too late. The image of a magnifying glass looking at a broken grid illustrates how we try to hunt for these errors, but the red glow of the opacity risk remains difficult to isolate. We must be aware that when we step into alien mathematics, we are subject to alien errors that our traditional debugging tools were never designed to catch. In page 14, we propose an architectural reframe, the lens versus the oracle. In the past, we might have viewed AI as an oracle to be trusted blindly. However, the next generation concept is to view AI as a lens for directed exploration. Your job is no longer to write the math yourself. Instead, your job is to build the instrument, point it at the dark areas of our knowledge, and translate what it finds back into human knowledge. The diagram shows a telescope focusing a field of scattered points into a structured blueprint. This is a shift in the role of the scientist and the mathematician. We are now tool makers and interpreters. We use these high-dimensional systems to see further into the universe than our natural eyes allow, and then we do the hard work of trying to map those discoveries back into a form that fits within our biological constraints. The final page, titled End of Run, The Infinite Horizon, summarizes our current position. The universe is speaking in alien mathematics, and the machine can reach much further than we ever could on our own. Our environment is now mathematically structured beyond biological limits, and our system status is online. We must embrace this new reality and build tools that help us catch up to the machines we have created. The grid stretching into the distance represents the infinite possibilities that lie ahead of us if we are willing to work alongside these high-dimensional architectures. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.